Now let us see how to find out what is called as higher order derivatives, which is nothing but say we have a function y of x. Now when we differentiate once, we get what is called as the first derivative, that is denoted by dy by dx as shown here. Now that derivative is also some function of x only in general, isn't it? So if we differentiate that further, we get what is called as the second derivative of y, and that is denoted by this particular symbol, that is d square y upon dx square. Now although we typically call it as square, it is not really the square of anything, it is just a notation, and that is called as a second order derivative. Now if you differentiate that further, we'll get the third order derivative and so on, right? Now let's see another notation also, that is, we know that the first derivative can be denoted by y dash, so therefore second derivative is denoted by y double dash and third as y triple dash. So we have various notations, as we know. Sometimes the derivatives are also denoted by the suffixes, that is y1, so then you will have y2 and y3 and so on. And if we use the f of x notation, that is if we denote y as f of x, then its derivative will be denoted by f dash of x, as we know. Then the next derivative will be denoted as f double dash of x and f triple dash of x and so on. So these are just notations to keep in mind. So remember that the higher order derivative is nothing but the derivative of the previous order derivative, nothing else. So first derivative is the derivative of the function. Now when we differentiate the first derivative, we get the second order derivative and so on, right? Now let us see few examples that involve second order derivative and higher derivatives. Okay, here we have to find second order derivative of y given as x raised to 6. Now if y is x raised to 6, therefore first calculate the first derivative, and it is nothing but 6 into x raised to 5 using the standard function. Now if we want to differentiate further, we will get the second order derivative, that is d square y upon dx square given by. So here we have to differentiate the first derivative. Now to differentiate that, 6 will remain as it is, multiplied by the derivative of x raised to 5, which is nothing but 5x raised to 4, isn't it? So that finally gives us 6 into 5 as 30 into x raised to 4. So that is the second derivative. Now let's go ahead and see one more question. If y is given as a sin x plus b cos x, then show that d square y upon dx square plus y equal to 0. So here we see that indirectly we have to find the second order derivative and show that it is equal to minus y. So if you take y on other side, second derivative will be nothing but equal to minus y, right? So let's differentiate y, which gives us dy by dx, that is equal to derivative of a sin x is nothing but a into cos x plus derivative of b cos x is equal to b into derivative of cos is minus sin, so that gives us minus sin x, which is nothing but a cos x minus b sin x. Now remember, a and b are to be considered as constant. Now what we have obtained is the first derivative. So let's differentiate once again, because somehow we have to obtain the second derivative. So d square y by dx square is equal to, now to differentiate a cos x, we have a into derivative of cos is minus sin minus b into derivative of sin is cos itself, so that is b cos x. So that is equal to, if we take minus sign outside, we will have in the bracket a sin x plus b cos x. So if you observe, the bracket is nothing but the original expression of y. So therefore a sin x plus b cos x can be replaced with minus y. So therefore we get the second order derivative to be equal to minus y. So obviously if we bring y on the left hand side, we will get d square y upon dx square plus y equal to 0. So that proves the required statement.